Okay, good afternoon, everybody. I guess I had a pleasure opening our working group, and I also have a pleasure to chair the last one. So we will start with a talk from Miguel, who will tell us about the measurements of lepton-jet correlations in DIS on behalf of H1 collaboration. We can see your slides. Can you say something, Miguel?
Yes, hello, can you hear me?
Yes, but now we cannot see your slides.
Oops, 1 second.
Yes. Okay, so you have 17 minutes. I will remind you 2 minutes before this time ends. Please start.
Okay, thank you. So today I will present a new result on lepton-jet correlations in deep inelastic scattering, and I will be presenting on behalf of the H1 collaboration. So this measurement is motivated by recent theory developments, which indicate that lepton-jet correlations in the back-to-back limit prove quark TMDs and their evolution. So this was proposed a couple of years ago by Liu et al. And Gutierrez et al. In these two PRLs. And the main idea is that you measure the imbalance between the lepton and the jet. If you measure that very well enough and in a differential manner, we might be able to prove TMDs with a new channel. So in particular, the focus of this measurement is the DIS Born level configuration, which is shown here on the left-hand side in a schematic way, and on the right-hand side in an event display. So you want to be able to have this back-to-back topology, where you produce only one jet that recoils against the electron, and measuring that allows you to probe the quark TMDs. And so this is a bit unusual because typically this Born level configuration was referred to as a background channel in previous measurements that actually target gluon initiated processes. So this is like a rethinking of this channel. Now, with the new theory developments, we think that this is going to be a very important channel for TMD physics. So let me just tell you a little bit more specifically what is the motivation for this. So in these two papers, the authors propose two ways actually that you can measure this type of reaction. You can use either the laboratory frame and reconstruct jets in that frame, or you can use the bright frame and also do the analysis. And the cross sections and the factorization formulas that appear in each case are slightly different. What I'm going to present today is the measurement using the laboratory frame. And so according to Liu et al., you can factorize the cross section in this form that you can see in here. And the main idea is that you are sensitive to the transfer momentum dependent PDF. So you replace the fragmentation function that would appear otherwise if you measured actually not jets, but single hadrons in this traditional series way of constraining the TMDs with PDF and other factors that are the hard function that is perturbative calculable and a soft function that carries the non-perturbative corrections to that. So that's the motivation for this. In summary, anyway. So another aspect of this measurement is that we not only constrain the PDFs, but also, and perhaps more non-intuitive, is that we need also to constrain the TMD evolution. And by doing this type of measurements, in particular at theta, we can bridge the low Q-squared measurements that are done in fixed target experiments and the high Q-squared measurements, Drell-Yan measurements that are done at colliders. And by measurements, I mean measurements that target TMD physics, like TMD sensitive observables. And so with this type of measurement and doing it with H1, we can really cover a wide range in Q-squared, bridging those two regions. And that allows us to really fix open issues, will allow us to fix open issues regarding TMD factorization and universality. This global analysis really mix or combine measurements at low Q squared, which are cities, with high Q squared, which are hadron collisions. And to the extent that you can do that, it depends on the degree of factorization, breaking effects, and universality. So this DIS measurements with H1 will allow us to really probe Q squared the Q squared dependence of these functions over a wide range, and also, of course, the low X dependence, the X dependence towards low value for these functions. And this provides a really an important baseline for the future electron-ion collider, because then we would be able to really better extract the functions and effects that we are looking for with polarized beams. So this H1 and Hera measurements is the unpolarized baseline that we absolutely need for precise and accurate measurements. So the H1 experiment at Hera is what we are using to do this measurement. So it combines a tracking system that has various technologies and liquid argon calorimeter with both electromagnetic and hadronic sections. And both of them are combined in an energy flow algorithm, which is what we use to reconstruct the jets and reconstruct also the kinematic variables of the DIS events. So of course, H1 is a mature experiment, and that means that actually the measurements of the lepton and jet are extremely precise, and the instrumental effects are very well controlled at this point. And so just to give you some numbers, 1% is the jet energy scale uncertainty, and the lepton jet scale uncertainty is about 0.5% to 1%, depending on the kinematics. So extremely precise measurements, which allows us to really use this data set to probe the physics, the new physics or the new developments in theory with a very known instrument. Let me just tell you quickly that we also use the sigma method to reconstruct the DIS kinematic variables. So the sigma method is described here in these two equations. So we use the measurement of all the hadrons in the event in order to constrain the inelasticity of the event and the Q squared combined with the lepton measurement. So that allows us to have better resolution in these variables, in particular in Y. But even if that's the case, the smearing effects in the Y variable are still significant and need to be unfolded. Just as a reminder, as a quick note, we don't use QED radiative corrections at this point in time for this particular preliminary result, although we're going to do that in the future. Let me just show you the jet performance. This is just from simulation. The jet performance that you obtain with the energy flow algorithm that is implemented in the H1 experiment. So I'm showing you here the jet energy resolution in orange and the jet energy scale in blue. The minimum PT that we are actually, then this is the PT in the lab frame, by the way. The minimum PT that we use or that we record at the unfolded level is 10 GeV. So this is just to give you some perspective of what is the resolution that we can reach at that PT, and of course it gets better and it reaches 10% at 40 GeV. So that's a figure of merit, and that we have for this analysis. And of course we need to unfold and correct for those effects. And what we are using, and this is the first time that this has been used for a measurement of real data, is the omnifold method, which uses machine learning to do an unfolding which is unbinned, and it works very well in a multidimensional way. So it handles the multidimensionality of our problem very nicely. And this is a figure that they took from their paper, and which illustrates what are the steps that are involved in the unfolding procedure. And I will not go into much detail. You can, of course, I refer you to this PRL paper, but I will describe that it has two steps. In one step, you make sure that the Monte Carlo at the reconstructed level matches the data. So there is a reweighting procedure. And then at the separate step, there is the unfolding procedure in the sense that the truth level information is used and reweighted, and the whole procedure, step 1 and step 2 are interlinked, and there is an iterative procedure, just like the Bayesian iterative procedure. This also has a number of iterations that we set to a reasonable number, like 3 or 4, and then it converges rather quickly. So let me illustrate what this means. So in here, the first step that we use the reweighting for the reconstructed level distributions, and this means that what I'm showing you on the right-hand side is 2 distributions that either use Django Monte Carlo or RAPGAP Monte Carlo. So that's the purple or the green. And the reweighting procedure in this omnifold method really makes sure that the Monte Carlo that you are using for the response matches the reconstructed data. So in here, I'm not showing you data, but I'm showing you the RAPGAP as a pseudo data. And you see that once you reweight the purple into the green, that is a black distribution that works very well. And that is not very impressive because you can do that in 1 dimension very quickly, very easily. You just take a ratio of 2 distributions and then you apply a multiplicative factor, and then you would get the same result. But the main idea behind the omnifold method and using the machine learning techniques is that you can generalize this to multiple dimensions. And so this is 1 example here where I show you various variables like kinematic variables and transverse momentum and other variables of the jet and the electron. And all of this can be actually reweighted simultaneously. So you go from the purple distributions to the green distributions, and that actually gives you a very good representation of what you actually measure. So that is, and this works in a multidimensional way, and it actually works in an unbinned way. I'm showing you here binned distributions just for visualization purposes, but the weighting itself is unbinned. So, and that's a step 1. But of course, we also have step 2, which is the proper unfolding procedure. And in order to convince ourselves that this is working as intended and to estimate what is the degree of bias that it introduces, we use a series of closure tests in which we use, for example, pseudo data Django and then the response RAPGAP, so 2 different Monte Carlos. And we know here what we should get from the unfolding, and then we compare what we expect with what we get with the procedure. And this is shown here for 4 different variables: jet transverse momentum, the imbalance, and the jet pseudo rapidity, and the jet azimuthal angle. And in all cases, you see that the unfolded result agrees with the truth level Django. So the black agrees with the orange, which means that this closure test is working or is converging. And the degree of which is shown here in more detail when you take the ratio of 2 distributions. So the non-closure is shown in the blue. So that's the degree of non-closure. And you have to compare that to the degree of difference between the RAPGAP and Django distributions to start with. So you start with some rather different distributions, and then after you do the unfolding and check the closure, you realize that that degree of bias coming from the prior distribution is very much reduced. And to the degree that it doesn't really cancel completely, we take that into account as in the systematic uncertainties of our measurement. But that closure is it's within 10% for all the intervals that we actually study. And of course, we don't just do this type of closure test. We also can invert. We can use RAPGAP as a pseudo data set and use Django to unfold. And we also did that, and we get similar results. So now I'm going to show you the preliminary results, which you can find here in this link, and the note that describes the measurement in perhaps a bit more detail. Let me see. Yeah, so the measurements that I'm showing you here are the transverse momentum and pseudo rapidity of the jets in in the laboratory frame. So on the left-hand side, you see the Jet-PT, which starts from about 10 GeV to about 100 GeV. And that is compared with fixed order PQCD calculations, which are multiplied by a hadronization correction factor, which is actually rather small for the Jet-PT case. And you see a very good agreement between the cross-section, which is actually normalized, the inclusive cross-section of jets, and over the entire range. Especially for the higher order contributions. So the green and the red in this curve. On the right-hand side, you see the jet fluid rapidity distribution, which is not as well described. So the Jet-PT here on the right-hand side is as a minimum 10 GeV.
Miguel, you have 2 minutes left.
Yes, thank you. And so we see hints of need of an NQ description. We also compare this with Monte Carlo generators, and the Monte Carlo generators do a rather good job for the most part, except in the fluid rapidity, some of them actually have some difficulty getting the exact shape. So this is the main result of this analysis, which is a Jet-QT spectrum, and we compare that with a TMD calculation, which you can see in purple or in blue, and the fixed order PQCD calculation is shown in green and red. The TMD calculation does a very good job describing the data at low Q values up to actually rather large values, close to QT divided by Q of 1. And then it starts to fail. And on the other hand, the PQCD calculation describes the data at large values rather well. And there is a big overlap between the two. And in the TMD calculation in particular, is not by construction that this calculation should match the higher order term. So using this data, we can actually help constrain it. So let me just tell you that this TMD calculation has no free parameters and describe the data over a wide range. And the TMD PDFs that were used to do the cross-section calculation according to this formula were extracted from low Q-squared data and Drell-Yan data. So this actually gives you a confirmation that the evolution effects and non-factorization issues are actually under control. We see qualitatively the same results when you use the azimuthal angle instead of the momentum imbalance. Similarly, the PQCD calculation describes the data at large values, fails at low values, where the TMD calculation describes the data rather well. And let me just tell you here that we also compared these two distributions with Monte Carlo generators, including Pythia, Django, RapGap, and Cascade. Cascade is a TMD-based Monte Carlo that actually includes TMD PDFs and the proper treatment in the shower. And you can
think about wrapping up your talk. Thank you.
Yes, and you see low values. It describes the data rather well. Summary. So we report the measurement of the lepton jet momentum and the azimuthal angle in deep inelastic scattering, which provides a new way to constrain TMD PDFs and their evolution. So you can see the degree to which those calculations describe the data is actually rather nicely described at either low or high Q-squared, and there is a big overlap which we can use to match the two frameworks. We also report the first ever measurement that uses machine learning to correct for detector effects. So this is a nice milestone, and we are using the omnifold method. So this is the first measurement on a series of measurements as we're going to do, which aim at creating a pathfinder program for the future electron lag. So thank you.
Thank you very much. And I open the discussion. Are there any questions to Miguel? Yes, I have one. On slide 17, you mentioned that your data hints for N3 allow corrections. Is there a possibility that this is next to leading order electroweak instead?
That's a good question. I think that is most likely is the next to is a NQ LO term that is missing, simply because this fluid rapidity has been measured before by SUSE and has been compared with NQ LO predictions, and it matches the data rather well. So we think that in our case, we will also have a nice agreement. It's just we didn't get those predictions in time for this conference. But the calculations exist, and they actually not negligible. And to the degree to which the electroweak effects that you're describing play a role or not, I don't really know for sure, but I suspect that this wouldn't be the case simply because the low Q squared.
Okay, any other questions? I don't see any raised hands, so thank you, Miguel, again.
I see Ignacio.
Excuse me?
I see Ignacio.
Ah, okay, I missed that. Please, Ignacio. Ignacio, you are muted. If you want to ask a question, you should unmute. Or lower your hand if you don't want to talk.
Is it fine now?
Yes, we can hear you now.
So I wanted to congratulate for Miguel for this talk. It's very important to have also Jet available for TMD. A comment about your last plot. When you started the NLL prime, do you refer to this the prediction of the Echevarria and so on? So how did you get this prediction from TMD?
Yes, I should have put this in here. This is indeed the framework follows this cross section, so which is Liu et al., but it was made by at the next to leading log by Youngbo and Kang, and he indeed used the TMD PDFs that are in here listed and then were recently tested in the Echevarria et al. Paper.
I understand. I think one can get a better job with other framework, but say, okay, it's fine. Great that you have this result. Thank you.
Okay, thanks a lot. So Miguel, if you could unshare your slides, we'll go to our next talk, which is Andrea, who will tell us about TMDs at Compass. Andrea, could you please share your slides with us?
Yes.
Give me 1 second, sorry. I am trying to unshare. That's it. Thank you.
Thanks. Okay. So Andrea, you have 17 minutes. I will remind you 2 minutes before your time ends. Please start. Okay. We can see your slides and we can hear you.
Perfect. I'm going to talk about transverse momentum dependent observables in unpolarized semi-inclusive deep inelastic scattering at Compass. So the cross section in the unpolarized case in series is made up of, can be written in terms of 5 structure functions that are listed here. So FUUT, FUUL, and then there are 3 structure functions that are related to the azimuthal angle phi h, in particular to the modulation with cosine of phi h, cos 2 phi h, and sin phi h. And this structure function, all these structure functions can in general be written in terms of TMD PDFs and TMD fragmentation functions. In particular, focusing on the unpolarized case, we have access to the number density TMD, so F1Q, which is function of X, Bjorken X, and KET squared, and on the Bohr-Mulder's TMD H1 perp, which is still unknown as still function of X and Q squared. Up to order 1 over Q, as I said, these structure functions can be written in terms of TMD. In particular, FUUT can be written as a convolution of F1 and D1, so the unpolarized PDF and fragmentation function, which also enter in the cos phi structure function in the so-called Kahn effect after Robert Kahn, who first introduced it. And then there is the Bohr-Mulder's term at the same footing in cos phi again. Bohr-Mulder's term, which also is dominant, which is dominant also in the cos 2 phi structure functions. By convolution, we mean convolution over the unobservables transverse momenta, so KT, the intrinsic momentum of the quark, and P perp, which is the momentum acquired during the fragmentation. So starting from this consideration, I'm going to present preliminary results about the azimuthal asymmetries, which are defined here. So the ratio of the angular dependent or related structure function over the angular independent, FUUT and FUUL, and the transverse momentum distribution, which allow to access properties of FUUT. So I'm going to present Compass preliminary results, and these come as a part of a large campaign of study of the nucleon structures, which included not only measurement in cities with unpolarized targets, and in this case, we also had measurements with a deuteron target for both azimuthal asymmetries and transverse momentum distributions, but also with spin asymmetries with transverse polarization of the target, and also longitudinal spin polarization. And this gave important results on the extraction of transversity for sure, and for the series function. So this is part of the results that I'm going to show are part of a large campaign on the study of the nucleon structure. So about the 2016 data that I'm going to discuss. So in 2016 and 17, the data taken was dedicated mainly to the measurement of deeply virtual counter scattering. There was a dedicated talk in a previous session. And in parallel, new CDS data have been collected with a high energy muon beam and an unpolarized liquid hydrogen target. This is at variance with previous measurement on deuteron. Now we have pure proton. Part of the data, so some 11% of the available statistics, have been analyzed to get preliminary results on the observables that I introduced. For both measurements, there is a need for detailed and refined Monte Carlo simulation for both the acceptance correction, and for this we used the lepton generator, and for the subtraction of the exclusive hadrons that I'm going to introduce, for which we use the Epstein generator instead. So what about these exclusive hadrons? By exclusive hadrons, we mean the hadrons that are produced in the decay of exclusive diffractive vector mesons that are particularly two channels. So the diffractive production of ρ, which decays into pi plus pi minus, and of phi into k plus k minus. These events are well visible in the data. In particular, you can see it from the plot on the right, which is obtained for a particular class of events in which exactly two hadrons are observed in the final state with opposite charge. And you see that there is a peak at zero, meaning that in the missing energy, meaning that the two hadrons carry all the energy of the event, and this is why we call them hadrons. The important thing is that their amount is strongly kinematic dependent, and this can be seen, for example, here in the plot on the bottom left, where you see that the fraction, their fraction can be as high as 30 or 35% at high z, seen as a function of pt, but seen as a function of x, z, or pt, we see that they are dominant at small x more than ix, and then again they are non-negligible for sure at iz, in particular for the negative hadrons with proton target, and also decreasing with pt. Also important is that they show strong modulation in the azimuthal angle, and this can be seen here. So Z is the fraction of energy carried by the hadron, and phi h the azimuthal angle. You see that at small z there is a strong positive modulation in the cosine of the angle, which turns out to be basically 0 at intermediate z, and then changes sign and becomes negative. So this contribution, which is non-series, has to be taken into account. It has been estimated and discarded, treated in the proper way in order not to contaminate the series sample. The impact on the azimuthal asymmetries has been taken into account and calculated also for the deuteron rate data in a recent COMPASS publication. So I'm gonna move to the observables that I introduced. So the azimuthal asymmetries, their definition has already been given. There are three steps basically in the measurement. The first is the treatment of these exclusive hadrons. So what we did is the following for the visible component, that is the fraction of the events that we are able to tag as exclusive, because we reconstruct both pions, say for the rho zeros, or both kaons from the phi are discarded, while the non-visible component, namely the events in which one hadron of the two is not is out of acceptance, this fraction is subtracted using the Epstein Monte Carlo. Then come the acceptance corrections and the fit of the amplitude of the modulation in the azimuthal angle of the hadrons that has been done either as a function of x or z or pt, so in one-dimensional approach, or with a simultaneous binning in 3D. So what I'm showing here now is the 1D approach. We have 3 rows for the cos phi, cos 2 phi, and sin phi asymmetry as a function of x, z, and pt, which are the 3 columns for positive and negative hadrons. We see strong kinematic dependencies, as was the case with the previous measurement on deuteron, both in COMPASS and also other experiments like Hermes. And we also see interesting differences between positive and negative hadrons, particular here, as a function of cos, for cos phi, you see it very well. They are very well separated. These results are, as I said, in 1D, so as a function of one of the 3 variables integrating over the other 2, and also are integrating over Q square, over our Q square range. But we also did the analysis pinning in Q square. So what we have here is cos phi, the cos phi asymmetry in 4 bins of Q square from 1 to 16 divided into 4. And we see a very interesting evolution with Q square, an increase in size, first of all, and then also an evolution as for the compatibility between positive and negative hadrons, which is not there at small Q square, but can be indeed seen at higher Q square. This evolution is indeed not expected from the easiest assumption that one can make, that is the flavor-independent Kan effect, according to which one expects a cos phi asymmetry which decreases with Q, because there is a proportionality to 1 over Q. So having a strong dependence, such a strong evolution with Q square and increase in size may be due to a strong dependence of the transverse momentum square, KT square on Q square, or can also indicate the relevance of other terms in the asymmetry. We know that there is Bohr-Mulder's, but can be others. So this clear dependence on Q square is can be seen also in for fixed x, so binning in x and seeing as a function of Q square, and this is shown here for 6 binning in x, integrating over the full Z range. Correlated to the Q square dependence is the W dependence by definition. Here we have again the asymmetry as a function, the cos phi asymmetry for 2 bins of W, so smaller than 12 and larger than 12, which is almost in the middle of our range. And again, you see a better compatibility between positive and negative hadrons at larger W, which is not really there at smaller values of W for both bins in Q square. In general, the consideration that I made on the evolution with respect to Q square and W are much weaker in the cos 2 phi case. So these are well visible in the cos phi asymmetry, but not there, almost not there in the cos 2 phi asymmetry. As I said, there are also the 3D extractions. So here we see, for example, the cos phi asymmetry as a function of x, and in bins of Z and PT, where we see again the trend with respect to x and also with respect to PT. The same has been done for the cos 2 phi asymmetry, and here we expect that the Bohr-Mulder's term is the most important, the dominant one, and this gives us confidence that a direct extraction of H1 perp, the Bohr-Mulder's function, is feasible, may be done. I'm moving to the second observables, which are the transverse momentum distributions that give for sure complementary information on the transverse momenta, KT and P perp with respect to the azimuthal symmetries, and are also interesting for TMD evolution studies. And there has been a lot of theoretical work in the recent years to reproduce the experimental distribution over large ranges. Of course, this I should have mentioned before, but on top of these 2 observables I'm discussing, there is the measurement of the cross-section, which is ongoing and will for sure give even more information. But for the moment, we have the 2 observables I'm presenting. So in Gaussian approximation and at small values of PT, the number of hadrons as a function of PT is expected to be exponential. So one expects an exponential trending as a function of PT, where the slope of this exponential is expected to be linear in first approximation with respect to KT square plus a term which is the p-perp square average. This exponential trend at small pt can indeed be seen, for example, in this case. So at small z between 0.2 and 0.3 for positive and negative hadrons. So what we are seeing here are the distribution of our hadrons normalized to the first spin in pt as a function of pt and in means of x and q square, where you see again, as I said, the exponential trend, which indeed is a double exponential when you look at the higher values of pt. So can be modeled with a single exponential up to 1, but that there is for sure a second component that is less prominent, less visible, going to higher z. So for example, in this case, this last spin of the 4 that are presented here, where basically the distribution follow a single exponential. These results are indeed in good agreement with previous deuteron results as for the trend and for yes, the evolution of the slope with z. As I said, a single exponential can be enough to describe the data as small pt, and this is done here with a single exponential fit to see the evolution of the slope with z. And I said before, one expects first approximation a linear trend with z square, which is not really there, not perfectly there, and this observation is indeed not new, was already there also for the deuteron data. So this confirms that there is a sort of a saturation effect at higher z. Of course, one is not forced to make a fit. One can simply take the average pt square from the sample of the hadrons that are being analyzed and see if the trend is satisfied. And this is just another way of saying that this is not the case with more beans instead, 7 instead of 4. So this confirms previous observations. As done for the azimuthal asymmetries, we are also working on the characterization of the kinematic dependencies. We know that there is the q square for sure that is expected from TMD formalism, from evolution, but also W dependency is interesting and present. And here I'm showing a plot from the EMC collaboration from muon proton, muon deuteron. So the average value of the transverse momentum as a function of W squared, you see, has a well visible slope, well visible trend. So we also for our data, we decided to characterize the dependence upon W by cutting at 12 and looking at the distributions below and above this value. So here is just a couple of examples of distribution that we have produced for W smaller and larger than 12. We compare them, taking their ratio, and also interesting is the evolution with q square. So if what happens if you take—
you have 2 minutes left.
Yes, I'm finishing. What happens if you take a fixed x and take the ratio of 2 bins in q square, how it looks, how it works, and if this is expected. This characterization is interesting and new. I'm moving to the very last slides by introducing a third, indeed, observables, which is, however, related to the second. So the momentum distributions, it is QT, defined as PT over Z, that is often indicated for TMD formalism studies, because we know that we expect the TMD to work at low QT over Q. So this distribution have been measured using the same samples selected for the PT square distribution and are shown here arbitrarily normalized and scaled for better readability, and in the same for Z bins. And what we tested and is shown here is that the distributions are in good agreement with an approximated formula that one can directly derive from the distributions as a function of PT. So starting from the distributions in PT, one can convert them to distributions in QT, and these are in good agreement with the ones that are derived or measured ex novo. This is also a good piece of information for phenomenological studies. I'm moving to the conclusion. So I've presented 2 observables in unpolarized cities that are particularly interesting for the TMD physics, that are the azimuthal asymmetries and the transverse momentum distributions. These are not new in the sense that COMPASS already measured them using a deuteron target. Now we have proton target and new results coming. for both observables, there are interesting and rich kinematic dependencies, which I have introduced and discussed briefly. So we think that this new data will bring new information, and they constitute a step forward in our understanding of the nuclear structure. So this is all. Thank you for your attention.
Thank you, Andrea, very much for very interesting summary of the COMPASS results and also for staying in time. I already see that Nobuo has a question, please.
Hi, I have a quick question and comment. So is all the measurements so far include this subtraction of the row peak, of the row decay?
Well, for the proton data, yes, we are starting it. We are subtracting the exclusive component as a very first step in the analysis. For the previous work, so the results, the azimuthal asymmetries on deuteron, there is a recent publication in which there is an estimate of the impact of this exclusive contribution to the already published and new plots with the azimuthal asymmetries, while for the PT distributions on deuteron, they were already taken into account. This is a publication from 2018.
Are you guys going to keep, produce the spectrum with the row? Because honestly, I really don't know how to do a theory without the row. So, the fragmentation functions do incorporate that information there. So it is a little bit difficult to sort of reconcile, the measurements where you exclude things out of the states, where in the theory, the correlation functions are summing over everything. Mm-hmm. And so do you have a sense of more or less how the spectra changes if you don't do this correction? Is it like a totally crazy thing, or? Well,
it depends on the kinematics, as I said. So at IZ, there is a strong contribution from the exclusive from diffractive row. So in that case, of course, the statistics is also smaller with respect to other bins, but in principle, they are there and they are not few. This is why we are taking them into account.
Okay, there's also
they are exclusive rows, not inclusive.
Was there a question or comment?
No, it was a comment to the question. We are excluding the exclusive, the diffractive row zeros, which I suppose are not in your formalism.
Right. So in principle, cities includes those channels too in the definition, right? Theoretically, if you exclude them, then it's no longer the ordinary cities.
I don't think that cities include diffractive vector mesons.
Well, maybe continue this on the chat because we have still some more questions here. Leonard?
Yeah, yes, thank you. So I just wanted to make a comment about slide, if I understood you correctly, slide 11, you looked at what you called the Q-squared dependence of this cos phi asymmetry. And I wanted to understand, are you able to fit it with that expression, the Q-squared dependence? Are you able to describe the Q-squared dependence with that formula? Is that what you were saying?
What I was saying is that an increase with Q, yes, an increase with Q is not expected unless you you let KT square be Q square dependent. So yes,
I see. Okay.
Can be fitted, but you have to leave that free. So a different KT square for different Q square.
Yeah. So I wanted to point out that there is no factorization theorem yet, and Q squared, therefore Q squared dependence for these twist higher power suppressed or higher twist observables like the Kahn effect. There's a very interesting paper by Alexei and Alessandro Paqueta and others where they kind of tried to assume CSS factorization concept for this observable, but that it's an assumption. For a long time, this has been an outstanding problem to describe the Q-squared dependence of power suppressed cross sections like this, higher twists. And anyway, it's of interest that you have some data on this now. So that's nice.
Thank
But
you.
theoretically, there's a long way to go, it seems.
Okay, thank you.
Okay, thank you, Andrea, very much. We will now continue with the next talk, and Bugra will tell us about the PDF sensitive new measurements from CMS. So if
Hello, can you hear me?
yes, I can hear you. We don't see your slides yet.
Coming up.
17 now that we can see them. You have 17 minutes. I will remind you 2 minutes before they end. Please
Sounds
start.
great. Thank you. So thanks a lot for allowing me to present the results on behalf of CMS experiment, including very fresh results. Don't worry, the title is too long, but the talk will not be that long, and I hope I will be on time. So it will be about WNZ production and Drell-Yan in general from CMS. So let me start with the usual snapshot of the standard model cross-section measurements from CMS. As you can see here, we are covering a wide range of cross-sections, like 9 orders of magnitude. And what you will hear today is the top left of this plot. And you can see that we have measurements in 7, 8, and 13 TV. And basically our calculations are following the measurements nicely. Now, diving into the details of this talk. So why are we interested in studying the WNZ bosons in LHC and with CMS data? So they are one of the best understood processes at the hadron colliders, and the leptonically decaying channels are among the cleanest final states experimentally, which allows us to probe the QCD effects that governs the kinematics basically of the process. And by that, we can probe to different regions of the phase space. If we look at the generic PT distribution, we can probe to the soft QCD effects, the non-perturbative effects, and in the high PT region, we can probe the perturbative part and also the transition region, which is important to link the two. These measurements also allow us to probe the electroweak parameters, couplings, etc. And as you see on the top right, we can build templates using Monte Carlo, and we can distinguish helicities for the W and measure them separately. Also, we can search for rare decay modes in general. And most importantly, they provide stringent tests of our calculations based on standard model. So here is a glimpse of what you will hear. I will summarize 5 CMS publications and 1 very fresh preliminary result. Please don't worry if you cannot click on it yet. It's not yet public, but it will be very soon. So let me start with the Drell-Yan mass measurement at 13 TV from CMS using the first data in 2015, namely the 2.8 femtobarn in the muon channel and 2.3 femtobarn in the electron channel. We carried out the invariant mass measurement in MLL between 15 GeV up to 3 TV. And here I show the recall level plots showing the distribution of the backgrounds, where in most of the range it's Drell-Yan dominated. Going to the unfolded results in the next slide. Here on the left, I show the electron channel in the fiducial phase space defined by the cuts, compared with the MSET and LO predictions, and on the right, the differential cross section corrected to the full phase space. And here also we compare the measurement with the predictions from Fuse, and we see that the results are in good agreement with the predictions from the standard model. Saying that, I move to the next analysis that I want to show today. It is the Drell-Yan differential measurements at 13 TV again, but with the 2016 data. And in this study, we have measured the cross-section inclusively using 20 million of dimuon events and 12 million of dielectron events. And we measured the inclusive cross-section. And also we did the differential and double differential cross-section with respect to the PT of the dileptons and also the phi star variable as well as the differential cross-section in rapidity. And here I show the differential cross-section in absolute rapidity of the Z for the combination of the two channels. As a continuation of this analysis, this is the very new study. So as said, we have plenty of data already in 2016 data period. And so we carried out the measurement of the PT in masses out of the Z peak. By studying this, we can observe the dependence on the scale, dependence on the perturbative and non-perturbative QCD effects on the scale of the event. And also we can test models that are based on the traditional Parton shower, as well as the new models with improved multiple Parton emissions, such as transverse momentum dependent PDFs and also the resummation. So what we do is we carry out the measurement in PT and phi star differentially in 5 different mass ranges for the muon and electron channels. So before diving into the results, let me show you some distributions in the reconstructed level, in the detector level. Here I choose the 3 mass bins, the one below the peak, the on-shell, and then the second bin above the peak, from 170 GeV to 350 GeV in dielectron mass. And here, 2 important aspects is that the TT bar background is becoming important in the high PT and in high mass. And for that, we are vetoing the events with including the jets. And another importance is the inclusion of the photon-photon scattering, gamma-gamma to LL process, broken down into fully elastic, semi-inelastic, and inelastic cases, as you can see on the top plots. And the elastic case being mostly concentrated in the low PT, having a visible effect there. So moving on to the results. So before discussing the results, I have to describe you the theory predictions we used to compare our results with. So as said, we have the matrix element plus Parton shower approach from the MatCraft 5 AMZ10LO sample, which is up to 2 partons at NLO and linked to PTI 8 for the Parton showering. Also, we have the TMD approach. We have 2 predictions. We have cascade, which is linked to AMZ10LO for the matrix element and using the Parton branching TMD method, and using PTS6 for the final state and hadronization. Also, we have the analytic calculation from Artemide, TMD based, and we compare the measurements with that as well. And finally, we have predictions from Geneva, that is NNLO for inclusive Z and including resummation at NNLL in the jettiness parameter. So it is important to note that the measurement is done in the fiducial phase space, which is using dressed leptons, and for Artemide, the QED effects are calculated by us using the MatCraft 5 AMZ10LO predictions. And you see in the pink without the QED effects included, and in the green after including the effects. And the Artemide validity region by construction is up to 0.15 times the 15% of the MLL. So here I show the inclusive, the PT differential PT LL for the on-shell. And it's important to note that this result is consistent with the previous measurement of the same distribution and supersedes it for this, supersedes that measurement for this distribution. Moving on to the results in the off-shell. So here on the left, I show the low mass, and in the middle, the first bin above the Z peak, and on the right, the next bin in MLL. And here we see that the AMZ10LO prediction is giving an overall good description of the cross-section, but it's failing to describe the low PT, and it's increasing with increasing masses. Whereas the cascade predictions, here it's inclusive Drell-Yan plus PBTMD gives a much better description in the place where we expect it to do in the low PT, and it fails at high PT due to missing higher orders in the matrix element. Artemide as well works perfectly and in basically all the mass ranges. And here we see that the Q defects is mainly visible for the low mass because of the migration from the on-shell. For Geneva, as we have seen also before, we see a harder PT spectrum, and it's mainly due to the alpha S choice. In this prediction, we are using the alpha S as the world average at the Z-mass. So talking about the uncertainties, to improve the uncertainties of the measurement, we also did a ratio measurement to the on-shell. Here on the left, I show the breakdown of systematic uncertainties for the low mass and the first pin above the Z peak. And by the way, it's important to note that the luminosity uncertainty, which is published last week from CMAS, is 1.2% instead of 2.5, and it also improved greatly our precision. And by taking the ratio measurements, we see that most of the systematics are canceling out, leaving us with from 2% to 1% of a total uncertainty in the bulk, and up to 10% in the edges in PT. So here are the results for the ratio. On the left, the ratio of the low mass to the on-shell, and the middle for the first pin, and on the right for the next pin. And here we see that again, AM7LO plus PTI gives an overall good description, but also in the ratio, the low PT part is not well described. Here the cascade describes the low PT part better, and also even though it's missing the NLO part, by taking the ratio, it gives a good description also in that region. Artemide is doing a perfect job again, and it's giving a good agreement, a very well agreement in the validity range that is marked in this plot. The gray band shows the invalidity range of Artemide, and Geneva as well, even though it predicts the absolute cross-section, a harder PT spectrum. When we look at the ratios to the on-shell, we see that we get a good description of the data. And also, since it's the only prediction that is including the NNLO, it gives a better description in the high PT part, showing the importance of including NNLO as well. So moving on to phi star, which is an alternate variable, purely angular based, which allows us to study the low PT part, at least for the on-shell in detail. And it provides an ultimate precision. Here I show the ratio measurements of the phi star. On the left, again, from the low PT to on-shell, on the middle, the next to next highest, and the highest bin on the right. But since the several bins are distributed over, it has less discrimination power between the models. So all the models agree well if you look at the phi star ratios. Finally, for the one jet case for this measurement, we also carry out the differential cross-section of dilepton PT for the Z plus one jet case. And by doing that, we can also study radiations that are not collinear with the incoming partons. Here again, we have the best descriptions from the MATGRAPH 5 AM7LO sample. For cascade, which is here a prediction based on AM-ZNLO at one jet inclusive and the Parton branching TMD method. It's giving a good description around the PT values of the jet threshold, but it's failing where the Z+2 jet and other components are becoming important, namely at the very low PT and also in the high PT. And for Geneva, it is the same. Although the the difference is not as strong as the previous case, we have a harder PT spectrum. So that finishes my Drell-Yan part. So let me move to the W sector. This is the measurement of the W. So 2 minutes. Okay, yeah. I'm almost done.
Thank you.
So this is a differential measurement of W rapidity, helicity, and also the double differential cross sections, as well as the charge asymmetry. Here we carry out also in the muon and electron channels with the given selections, and we are vetoing extra events with extra leptons to clean for backgrounds, and also we have the transverse mass cut. And the measurement is carried out using a template fitting technique. As you see here, we build templates using the simulation, and we fit our data. And here I show the unrolled ETA PT bin. So each block is a PT bin, and each small dot is the ETA bin of the leptons. And here you can see the contribution of the left-handed and right-handed helicity states, as well as the longitudinal. And you can see that it's almost background free. So we also measured the total differential, total fiducial cross section for the W plus, W minus separately, as well as the ratio of the two, as shown here, and all agrees well with the MATGRAPH 5 AM-ZNLO predictions in the fiducial cross fiducial region defined by these selections. Here I also show the differential cross section in the absolute rapidity of the W's for the different helicity states, and we see a good agreement here as well with the AM-ZNLO predictions. Finally, showing the double differential cross section with respect to the PT of the lepton and the eta of the lepton on the top. Here we can see that on the low PT part, we are mainly dominated by the PDF uncertainty in the predictions, and when we go to the higher values, the scale uncertainty is also becoming important. And finally, the differential charge asymmetry with respect to the PT and eta is shown here in the unrolled pins, and you can see that there's some tension in the high eta pins. So this is the last topic that I want to cover today. It's as said in the beginning.
Wrap up, Bugra.
Okay. So we could also search for rare decays of the W's in the pions, and we set limits here. And this motivates also a calculation of direct branching fraction of these exclusive decay modes. So coming to my summary, I mean, I have already summarized during my talk. So by doing these measurements, we provide stringent tests of our models, and we can probe perturbative and non-perturbative QZ effects. And as usual, please stay tuned, more to come. Thanks a lot.
Excellent, thank you very much. That was a very nice summary of the results, and also almost in time. So I'm opening floor for questions. I see Patrick has a question.
Patrick or Pavel?
Yeah, I saw also Patrick. Okay, Pavel, go ahead. If Patrick has a question, he can be next.
Yeah, thank you so much for this very nice presentation. Can you please go to slide 14?
Sure.
So just a quick clarification. You said the 5-star rated distribution is not as discriminating between the models as the PT distribution, but in fact, here you're looking at the ratio of the 5-star rated distributions. Presumably the 5-star rated distribution itself is as discriminating as PT, isn't it?
Also for the off shell, it's not as discriminant because you can imagine phi star as PT over M variable, and with increasing masses, the mass becomes more dominant and it squeezes the distribution to low values. I mean, the public results will be there in 1-2 days, and
okay, thank you.
We can also iterate.
Okay, are there any other questions? I can see no more raised hands, so thank you, Bugra, again. Thanks. And we will go to the next talk, will be Patrick telling us about the Pion TMDs.
Hello.
Hello, please. Yes, I can see your slides. I can hear you. So I think we can start. You have 17 minutes. I will remind you when there are 2 minutes left.
Perfect. Okay. Sounds good. Thank you very much. So I appreciate for the organizers to give the opportunity to present my results here today. So I've been working a lot on the phenomenology of pions. And so today I'll describe my work with the Pion PDFs using systematic extraction of threshold resummation, meaning there's more than one ways to do threshold resummation. And then additionally, kind of on a different note, I'll talk about the applications and Pion TMDs and the current works with that. So this is a global analysis work, and so we need a game plan for how to proceed. And so first what we do is we define a structure of hadrons in terms of quantum field theories, and those exist for PDFs and for TMDs. And then we can identify theoretical observables that do factorize into non-perturbative objects and perturbatively calculable physics. So the non-perturbative objects are the PDFs and TMDs, and the perturbatively calculable physics we can do. And then from there, we can perform the global QCD analysis. These structures are universal and the same in all subprocesses. So specifically, my work has been with really the Pion, and the Pion is a very important particle. It's the Goldstone boson associated with chiral symmetry breaking. It's also the lightest hadron, while simultaneously being a constituent of Q and Q bar constituents. So you can see on the right is a picture of a Pion and a kind of QCD picture where you have valence structure of U and D bar quarks, and then we have C quarks and gluons also contributing to the total momentum of the Pion. So there are in our JAM analysis, we have 2 experiments that we use to probe the Pion structure. The vast majority of this talk will be focusing on the Drell-Yan process. And so what I show here is that the Drell-Yan, we have a Pion beam incident on a nuclear target. And I show the leading order diagram here. So that's a quark, quark coming from one of the hadrons and an anti-quark coming from the other, annihilating, forming that virtual photon, which decays into the detected dilepton. So this is the leading order diagram, and that's the most important in the perturbatively calculable physics. And then additionally, we look at the leading neutron data, which is a tag deep and elastic experiment. And what happens there is a electron beam is incident on a proton target, barely striking the surface, and knocks out a pi plus and a neutron, where the neutron is detected and carries the majority of the momentum of that proton. And when that pion is split, the virtual photon breaks that up. So effectively, we have a deep and elastic scattering on a pion through this leading neutron Sullivan process. So let me speak about the kinematics for these kinds of experiments. So we have Q squared versus X pi here, where X pi is a good proxy for like the Bjorken X for the Pion PDFs. And so what we see here is in the red circles is really where the Drell-Yan data live. So this is all at high X. And so the Drell-Yan is good at constraining the high X PDFs, namely like the valence PDF. However, the Drell-Yan does not do a good job of constraining the low X PDFs because there's no data there. So all that would be extrapolation beyond this X pi of around 0.1 or 0.2. Luckily, we have the leading neutron data available, and we make use of that, which do live at low X. And so we can get a picture of the Pion PDF both at high X from the Drell-Yan and at low X from the leading neutron, where the leading neutron really has the ability to constrain these C quark and gluon PDFs at low X. So we performed this analysis at next to leading order in 2018. And what we see here is that in the lightly shaded bands are the extractions using only the Drell-Yan data. So below at a low X pi, The C quark and the gluon distributions are not really constrained well, so they have large uncertainty bands. But when we include the leading neutron, we have this solid bands, which actually have the ability to constrain the gluon and the C quark distributions. Additionally, there's some model dependence here shown by the yellow, which is from the splitting from the proton to the pion and neutron. That model dependence is quite small in the available data. So what I want to focus on here in the first part of the talk is the threshold resummation that we apply. This is applied only on the Drell-Yan data, the Drell-Yan partonic cross-section, and it's focusing on the QQ bar channel, because like I said, that's the most important, that's the leading order, and the corrections on that channel will be the most important corrections to look at. So fixed target Drell-Yan notoriously has a large XF contamination of higher orders, meaning that there are some large logarithms that could potentially spoil the perturbation in fixed orders of alpha S. So our goal at the QQ bar channel is to resum all contributions of all orders of alpha S. So what we see here is kind of a quark line coming in, which radiates very soft gluons, and those soft gluons have the majority of the effect of these large logarithms. So the first place that you can see some correction is at next to leading order. And so that correction appears here as alpha S times log of 1 minus Z with the plus prescription. And that gets really mapped into the alpha S times log of 1 minus tau, where tau is Q squared on S, where Q squared is the invariant mass of the virtual photon squared, and S is the incoming center of mass momentum squared of the hadronic system. So in fixed target Drell-Yan, this tau can be large or close to 1. And so when you have this alpha S times the log 1 minus tau, that could potentially spoil the perturbation if that is not very small. So we can make improvements by resumming all of these terms that go as this log of 1 minus Z with the plus prescription. In practice, the threshold resummation is done in Mellon space, which is conjugate to tau. And so those large logs of 1 minus tau get mapped into large logs of n, which is the Mellon conjugate. So in a fixed order analysis, what we would do for the perturbative calculation is to sum up all of the rows, namely the orders of alpha S. So at next to leading order, we would sum up all the orders of alpha S and the leading order. With the inclusion of threshold resummation, what we want to do is we want to sum up the towers of the logarithms. And so you can see here in the leading log column that there's orders of alpha S to the K, log of N to the 2K. So that's the kind of perturbative expansion that we like. And so we can sum up all of these terms in the towers. Additionally, the results that I show are NLO plus NLL. So we also have a few subleading logarithms there. You can also see in the yellow that there's a overlap of the region. So when you're performing the calculation, make sure to only count that those terms once. So theoretically, I mentioned that there's some different ways of doing the threshold resummation. So theoretically, let me just point out why that is. So when performing the calculation, like I said, you have to do this in Mellon space, and you do a Mellon transform of this plus function. And when in doing so, you have this integration over K perp squared, where alpha S is evaluated at K perp squared, as well as this Z integration. So the upper limits, what you can see is that when Z goes near 1 and K perp squared goes 1 minus Z squared Q squared, that implies that this K perp squared is the alpha S is evaluated at 0, which is not well defined, and what is known as the Landau pole. So there's an ambiguity in how to deal with this. And so there's needed for prescriptions for how to deal with this in threshold resummation. In practice, what we do is we approximate the Mellon transform, and when inverting back into momentum space, we can avoid the Landau pole because this can be mapped out into Mellon space exactly. So this is known as the minimal prescription, and so that was invented by the Catani in the 90s, and this is what we make use. Another complication on top of that is actually the rapidity distribution. And so the data for the Pion data are in doubly differential, Q squared and rapidity Y. And so we need to also have this in conjugate space for that cross-section. And so in doing that, we have we can perform a Mellon Fourier transform, where the Fourier transform accounts for the rapidity. And in doing so, in there's actually another added step of complication. And so there's a cosine that appears where the argument of the cosine is near 0. And so you can you can take the first order expansion where cosine is approximated as 1. And in this analysis, I call that the expansion method. Additionally, you can keep the cosine completely intact. And so I call that the cosine method. Instead of doing the Mellin and Fourier transforms, you can do a double Mellin transform. And so that's an additional way to do it. So what I do in this analysis is I implement the 3 different ways: the expansion method, the cosine method, and the double Mellin method. And I perform the Monte Carlo global QCD analysis on the Pion PDFs and analyze the effects. So what I show here is the data and theory comparison for the Drell-Yan. And what I show for comparison here is the next to leading order in red, cosine in green, expansion in blue, and double Mellin in yellow. And I show this as data divided by theory. See the comparison of data and theory. So what we find is that at low XF, low Feynman X, that these all of these prescriptions more or less give the same result. But when you look at high XF, namely above 0.8, for instance, you can see that here the red and the yellow gives something that's along the same lines. And then the cosine and expansion tend to overpredict the data. So here we can see that clearly there is a large XF effect, and that is where there's major differences between these methods. So those large XF effects really get mapped into the large momentum fraction of the valence distribution for the PDFs themselves that are extracted. So in the top row is the PDFs themselves. And so most importantly is the valence distribution at high X. So I have this inset here to show that. And what we find here at next to leading order, this is a very hard fall off at X near 1. And then once you include the threshold resummation, that fall off gets much softer. And you can see here that there's varying degrees of how soft it can fall off. Additionally, what I show on the bottom row is the truncated moments. And so what this means is that where do the flavors themselves gather their momentum fraction? And so you can see that at large X, the valence distribution from the next leading order, fixed order, rises here, but once you include threshold resummation, that gets suppressed at large X. So all this large X momentum fraction from the valence distribution actually gets mapped down into the low X gluon momentum fraction shown here. We can also describe the large X behavior of the valence distribution through this effective beta parameter. So the valence distribution goes as 1 minus X to the beta as X goes near 1. And so what we see here is that the next to leading order shown in red is consistent with a beta parameter of 1. So 1 minus X to the 1 power. However, when we implement these different threshold resummation prescriptions, we find that there is no universal behavior for this beta parameter. So that, for instance, when you use the double Mellin method, get a much more close to linear behavior than you would if you use the cosine or expansion methods. So there's a wide range here shown for the beta parameter, and there is no universal behavior. So let me switch gears a little bit and move into the transverse momentum dependent Drell-Yan. As is known, the spectrum of the cross-section with respect to PT varies in theoretical treatment. And so at small PT, there's the TMD factorization, which is really describing from the partonic transverse momentum inside of the hadron. And that large PT, there's collinear factorization, where the large PT of the lepton pair really is coming from a recoil in the process. And so there are 2 factorization theorems here that would break down when bleeding into the other region. So you can see here, the TMD factorization have errors related to PT on Q, where the fixed order has errors related to M on PT. So we performed an analysis at next to leading order for the large PT distribution with the Drell-Yan data. That follows completely collinear factorization, so the PDFs are directly involved right there. And so you see here, we do have a QQ bar annihilation, but this virtual photon gets its transverse momentum from this recoil kick coming from that radiated gluon. So the gluon comes in at leading order for this large PT-dependent Drell-Yan data. And so what we found is that data does not really dramatically affect the PDF. It's almost the same as if you had a just a Drell-Yan PT integrated and leading neutron extraction, because those uncertainties on those data are quite large. And so we actually do get a successful description of the data with a scale as mu is PT on 2. Additionally, with the small PT region, we can use the CSS formalism for the TMD evolution, which we have here, which is basically 2 TMDs multiplied together. And what I highlight here in boxes are the non-perturbative TMDs that needed to be extracted. So these are the G sub J from the Pion, for instance, and the G sub J from the target, and then this universal G sub K. So what our approach here is at leading order with all these kernels and coefficients to use that leading order and diagnose what the current situation is.
Patrick, you have 2 minutes left.
Okay, very good, thank you. So what I do here is we perform a simultaneous fit of the small PT TMDs to both the E288 Drell-Yan data and the E615 data. And the reason that we do that is because in E615, it's Pion on a nuclear target. So you need to have some notion about what that nuclear target's TMDs are. And so we can gather that information from this E288 proton nuclear data. So what I show here is the simultaneous fit. This is just the, right here is just the E288 data. And so the red points is what we fit. And we get a good description as shown by the blue curves here with the data. And additionally, what I show in the green is the fixed order prediction. If we use just using the collinear PDF and the collinear factorization and using a scale of mu as PT on 2, which was found in the Pion case. And so additionally, this is the Pion data. And so you can see here at low PT, there's also good agreement with the data from our blue curve, which was the W term. And then these other high PT red points, those were previously already fitted. And so those have, we already knew what the situation was. So in the future, we'd like to further investigate the high X behavior of the valence PDF through constraints from using the lattice data. Additionally, we can perform a simultaneous extraction of the Pion PDFs and TMDs from both this large PT region and the small PT region simultaneously. And we would like to also explore the matching procedure between the W and the fixed order terms in the PT spectrum. As we can see, there's a hope for that based on the agreement in this middle region. So with that, I conclude. Thank you.
Very good, thank you. This was very interesting and also well in time. So I'm opening discussion. Are there, oh, sorry. That's your time running out. So you were just before. Are there any questions to Patrick? I don't see any raised hands, but if anybody has a question, please speak up.
So Patrick, maybe I can ask a question since, well, there were no other questions. To really discuss this matching procedure between W and fixed order terms, so you have to have a large enough range of PT spectrum. But like, for example, if you work at low energy Drell-Yan, you really don't have enough room for developing, well, proper Parton showering, if you like. So then what do you have in mind here? Do you expect some high energy data to do that, or you just still thinking about these fixed target experiments?
I'm still thinking about the fixed target experiments, namely because our focus is on the Pion, and the Pion data is all in fixed target. And so using that regime to kind of see that, I think that's a very good question and very open theoretically.
Okay.
Okay, there's a question from Leonard, please.
Yeah, this is Leonard. Hi, Pavel. I'm responding a little to your question. So in the plot that Patrick has right now, right there, with these E615 pi tungsten data, it's not inconceivable that even with this somewhat small region, where in many cases people just stitch the two regions together, that we actually could have an asymptotic term that interpolates between the two. This is our goal. Actually, okay. as Patrick said, we're diagnosing this. We're not saying we have a solution. But I appreciate your point. some people might argue that that overlapping region that he's displaying there, of course, it's on a log scale, might be enough to have the matching happen. As you know well, at high energy it works, and as you mentioned, for low energy, low PT experiments, it's been a great challenge.
Yes. Well, I hope you can do, because this is very beautiful data if you think about it, and so really, so it can teach us a lot. Yes. Right.
And in fact, this is the kind of data that we're really trying to diagnose CSS. A lot of people have worked hard, with different varying versions of the W term, and we're trying to just use the basics, and so we don't over-engineer things just to diagnose this problem, because it's been persisting, as you know, for a while.
Right. Okay, thank you.
Yeah.
Okay, very good. Any more questions to Patrick? If not, then I suggest we move to the last talk. Patrick, if you could unshare your slide, the last talk of today, and it will be Avanish telling us about DIS and N4LO. So sounds very futuristic to me, but please share your slides with us. Avanish, are you there?
Right. Yes, I'm here.
Yes.
Can you hear me?
I can hear you. I can see your slides. You have 17 minutes, and I will remind you 2 minutes before your time runs out. Please start.
Great. So hello. First of all, I want to thank the organizers for giving me the opportunity to share my work at this conference. So my name is Basdew-Sharma, and today I will be presenting some efforts towards calculating DIS at N4LO. This is a project which I've been doing together with my supervisor, Franz Herzog, and also with a postdoctoral group, Andrea Poloni. But on top of that, we've been collaborating together with Andreas Vo and with Jos Verhazen. Now, our grand goal is to calculate DIS at N4LO and also the for-loop splitting functions. But this is very, very, very hard. So therefore, we have set some intermediate short-term goals. First of all, we want to validate our algorithm, because we have to make sure that it actually works. Then we want to check some known VLOOP results from the literature. So we want to check the DS coefficient functions. But there also still are some unchecked results at VLOOPs, for instance, the polarized splitting functions. Now, here you see a plot from Atlas from round 2 at 13 TeV. So these are experimental data points, and this is the theory. And it is expected that at the high luminosity collider, the experimental uncertainties will decrease. So as you project in here. Now, these decreasing experimental uncertainties in their turn will require better theoretical predictions. So for round 2, the experimental uncertainties for Higgs production, sorry, the plus for Higgs production, they were around 8%. And then we expect the experimental uncertainties to be around 3% at the high luminosity collider. Now, these experiments will require theoretical predictions at N3LO. An important ingredient in those predictions are the for-loop splitting functions. Another point to make is that to obtain better Parton distribution functions, we will require better extraction of DIS data. So these are two motivational points for us, but of course there are other motivational points to be made. Now let's talk about our setup. Here in the left part of this diagram, we see the hadronic tensor. So this is the photon, this is the proton with a gluon and 2 quarks. Now, by using the optical theorem, we can relate the hadronic tensor to the forward scattering amplitude, which is the total diagram over here. In this talk, we will focus on the partonic section of this of these types of diagrams, because we want to calculate the coefficient functions. So what is our method then, you might ask? Well, it is known that we can reconstruct the coefficient functions from a finite number of meta-moments. Therefore, we want to obtain the many moments in a recursive manner. To do that, we will reduce all our systems to a limited subset of master integrals. After that, we will exploit the differential equations of these master integrals and also exploit their analytic structure. So let us now take a closer look at the force carrying amplitude. We can write the force carrying amplitude in the following way, where the coefficients T1 and T2 depend on the inverse Bjorken parameter. Now, the coefficients, they have branch cuts for omega going from -infinity to -1 and for 1 towards infinity. By using Cauchy's theorem, we can relate the derivatives at the origin to contour integrals around the origin. Subsequently, by deforming the contour integrals in the following manner, such that it encompasses the branch cuts, and then also by using the symmetry of the constants such that we can map the left-hand side to the right-hand side. So by using these identities, we can relate the coefficients to an integral over the discontinuities of the coefficients. Now, the discontinuity across the branch cut is exactly the imaginary part of our forward scattering amplitude. And by again using the optical theorem for even n going back to x, we can finally relate the coefficients to the Mellin moments. So as I said, it is known that we can obtain the full omega dependence for the coefficient functions from a finite number of Mellin moments. And this is done before by Sven Moch, Jos Vermaarse, and also later on with Andreas Vogt. So in 1999, in 1999, they did the two-loop calculation, and it took them 5 more years to do the three-loop calculation, first for the non-singlet part and then for the singlet. After that, it took Sven Moch and his collaborators 13 years to obtain partial results for the four-loop splitting functions. They obtained the non-singlet part in the planar limit, but they used an operator product expansion. A year after that, Sven Moch and his collaborators also obtained some four-loop results. So they obtained the four-loop splitting functions, but only numerical approximations in the singlet sector, using moments smaller than n(10). And in the same year, Franz Herzog and his collaborators obtained some results for the five-loop splitting functions, but only for the ns2 and 3 moments of the non-singlets. And there they used the R-star method. Now the takeaway message from this is that we will exhaust the analytic behavior of these functions at omega 0. Therefore, let us continue to our recursive algorithm. At one loop, it happens that we only have to consider one particular topology, which is the topology you can see over here. It is defined as such. Now, using integration apart identities, we can reduce all the functions in these topologies to a limited subset of master integrals. We've done this using the program Kira. It happens to be that there are only 2 masters for this topology, M1 and M2. Subsequently, we want to derive differential equations for these master integrals. But because M1 does not depend on omega and also therefore does not depend on P, it is not part of the system. For M2, however, we obtain the following differential equation. Then we will use a series solution ansatz for M2 to solve this differential equation. Now, notice, however, that the left-hand side of this equation, that for the left-hand side, for a fixed omega, it will always be 1 level higher in n than the right-hand side. Also notice that this prefactor, which I'll call the differential matrix, that it does not possess a pole in omega. Therefore, we are able to finally obtain a recursive algorithm for the coefficients. And with this recursive algorithm, we can iteratively build up the master integral. Now, of course, we need to have a boundary condition. And this boundary condition is obtained by taking the omega to 0 limit, which in this case exactly turns out to be M1. So great. Let's tackle the for loop problem, you might ask. Well, if it only were to be that simple, because there arise 3 different problems. First of all, what do we do with the boundaries? Is it possible for us to calculate them? Second of all, we found that the differential matrix actually does possess poles in A, which we did not expect a priori. And then third of all, we are not quite sure whether we can actually do the full reduction at for loops. But let us now first tackle the first problem, the boundaries. As I said, the boundaries are obtained by taking the omega to 0 limit. This corresponds to taking the p to 0 limit. But by taking p to 0, one will always obtain self-energies. And luckily for us, the self-energies up to for loop have already been calculated by Jos Vermaaseren and his collaborators, and also been stored using the program forcer. So this is very convenient for us. Thus, problem 1 solved. What about the second problem? Poles in a differential matrix. Now, we can always write a differential equation in the following form, where Aij is a differential matrix. Suppose now we have a toy topology with 3 masters, in which the differential matrix has a 1/omega to the 4th pole, 1/omega cube pole, and also 1/omega pole. We want to scale away all the poles up to order 1/omega. To do that, we will transform the masters using a T matrix, using a transformation matrix. And because of that, the differential matrix will also transform in this way. So let us now first remove the highest order pole, 1/omega to the 4th pole. We choose the transformation matrix T as a diagonal matrix in which the ith entry equals the negative exponent in omega of the highest order pole in the ith row of our differential matrix. So if we choose it in this way, our A matrix becomes this matrix over here. And as you can see, it no longer has a 1/omega to the 4th pole. However, we still have the 1/omega cube pole. Now, let us do the same thing for the 1/omega cube pole, choosing a new differential matrix, choosing a new transformation matrix. We then obtain this differential matrix, which no longer has higher order poles, but it still has 1/omega poles. And unfortunately, it is impossible to scale away these 1/omega poles in the same manner. Now the final transformation matrix looks as follows. And as you can already tell, the second mass will now start at order omega to the 4th, and the third master will start at order omega cubed. We conjecture that the diagonal T matrix is sufficient to map away the deeper poles from the differential matrix. Now, note, however, that this is still a conjecture. So far, we have always observed this behavior, but we have not yet been able to prove this conjecture. Now, what about the 1/omega pole, you might say? Well, it turns out that it is convenient to pull out the 1/omega pole from the differential matrix such that we obtain this differential equation. So this is general. We can always obtain this equation where the A matrix now no longer possesses any poles in omega. And using similar arguments by using a series expansion method for the masters, but also for the differential matrix, we can now obtain the following recursive relation, where C's are the coefficients of the masters. So notice that the left-hand side on the left-hand side, the K will always be larger than the K prime on the right-hand side. So we can always obtain this recursive relation to build up the masters in an iterative manner. B is defined as follows, where A0 is the 0th order of our differential matrix. We have implemented this in form in a very efficient manner, and it is also highly parallelizable. However, there still is a caveat for B, but let us not go into that. So, second problem also solved. Then what about the reductions? Or maybe it is better if I just show you some intermediate results. For the non-singlet, we have at one loop only one topology. At two loops, we have three topologies. At three loops, we already have 32 topologies. And at four loops, we have 364 topologies. So as you can see, this ramps up quite fast. What about the reduction time, you might ask? Well, at one loop, the reductions took us 3.7 seconds. At two loops, it took us 90 seconds. At three loops, it already took us around a week. So who knows what will happen at four loops? Likewise for the number of masters. At one loop.
We have 2 minutes. So
Right.
it's well below the time for four loops.
At one loop, we only have 2 masters. At two loops, we have 31 masters. But at three loops, we already have 3,000 masters. So again, who knows what will happen at four loops? Now, I must say that so far, the toughest recursive calculation was for topo 31 at three loops, a system with 156 masters, in which it took us 10 hours to calculate 100 coefficients on 85 cores. But to be honest, I think that this is still quite fast and efficient. Now, we are unsure whether we can do the for loop reduction on Tora. So Tora is our own machine with 64 cores and 1 terabyte of RAM. However, we are quite certain that we can at least do the order NF squared pieces. And I must also say that we are collaborating together with Johan Vucevic, who is the author of Kira, to implement new methods which might speed up the reduction. Thus, the reductions are still under investigation. So we went over some background of DIS, where I related the many moments to the force scattering. And after that, I told you a bit about our recursive method, about the IBP reductions, about the differential equation methods, the zero solution, and also how we transform the system and modify the recurrent relation. Right now, we already finished the calculation up to 3 loop for the masters, but we still need to put everything together and check against the previous results. And we're quite hopeful that we'll be able to start the for loop reductions in the near future. Thank you for listening.
Thank you very much, Avanish, for a very interesting talk and also for staying in time. I think if you do as well with time for your calculations as you did for the talk, then you are on a good track.
Well, let's hope so.
But that doesn't look very optimistic if you look at time, fortunately. Are there any questions? Oh, you see your time running out only now. So are there any questions or comments?
Hi, I'd like to ask a question. May I?
Absolutely, please go ahead.
Do you have any help from n equal to 4 side? For example, when we write down anomalous dimensions, anomalous dimensions, there is ordering in transcendentality, with the leading transcendentality agrees with n equal to 4. So do you have any ordering, do you expect to have any ordering in transcendentality here or not in the coefficient function?
To be honest, I wouldn't be able to tell you. I'm not sure.
But you when you're calculating anomalous dimension, it's naturally, I think, well, not naturally, but it comes out, yes? So n equal to 4 is maximal, then there are only smaller transcendentalities. So you don't expect such ordering here, no? We don't know.
I'm not sure.
Okay.
Yeah.
Are there any other questions or comments? Okay, I don't hear anybody. So I wanted once more to thank all the speakers of all the sessions very much, because the talks were absolutely interesting. And also, I think everybody tried to stay in time. Discussions were lively. So I think we could not expect more from our session. So this is a big thank you to all the speakers and participants from all the conveners. And this way, I am closing the session for today. I'm suggesting that everybody now has a drink, alcoholic or not, for a very successful working group 1 session. And I see you tomorrow for the plenary talks. Thank you very much and see you tomorrow. Bye-bye.